All right. Our next speaker is Richard Phillips, and he'll tell us about interpretable active learning.
Is this the one that... Does this work? Oh. Oh, shoot, that's... Hi, I'm Richard. Today I'm going to talk to you about joint work with my colleagues Hyun, Chang and Sorelle Friedler at Haverford College, titled Interpretable Active Learning. Before I get too into things, I think I should give some idea of what active learning means. So I'm going to try to do this with an example. So say I'm a chemist. I used to be a chemist. I'm a reformed chemist. And I have a bunch of ideas for reactions that I could perform, and I want to know if this certain drug works. And I have a bunch of already labeled, what we would call it, examples of different drugs that I've tried to synthesize, and I know if they work. And I want to pick out, this some subset of these unlabeled drugs that I could synthesize, and I want to synthesize them and train a model on it. And I want to improve my model as much as possible while synthesizing as few new drugs as possible. So sort of in a more abstract sense, we have a labeled data set, we have an unlabeled pool that we can select some limited budget from, and based on that, we want to pick the points that we can label that will improve our model as much as possible in as limited a time as possible. So there are some natural questions that I think follow from this in terms of interpretability. The first being, why is a query relevant? So if I'm a chemist and my, whatever active learning strategy I pick tells me, do this reaction, I have to spend a couple hours on it. It might cost me, 20, 30 bucks. Like, I might want a little bit of an explanation of what I might hope to learn from doing that reaction. It might look just like a bunch of other reactions that I've done. And even though that there are these guarantees on expectation of sort of how much my model will get better, I'm going to want to know, sort of in a human interpretable sense, how my model might improve. The other natural question, I think, is what is a model exploring over the long term? So this is not to anthropomorphize the process too much, but just sort of, are there trends that we're picking up, strengths that we're gaining over time, and can we relate that based to the things that we're exploring? And the third thing is, sort of if I'm, especially with like a social science problem, am I using active learning? It's not like a study. It's not a random sample. So am I ignoring or highlighting certain subgroups, especially protected classes that I might be interested in? And is that, doing so in a problematic way? So the big backbone technology that I have to introduce here is the locally interpretable model agnostic explanations framework. I think I got that all right, LIME for short. And LIME is basically a strategy based off the assumption that you can't explain a global decision surface simply. So if I have some 1,000 dimensional problem and a neural network trained on it, I can't give you 3 or 4 sentences based off, like that gives you an idea of how it makes its decisions. So instead of trying to explain the global decision surface, we're going to try to explain a local decision surface. We're going to perturb a point, which means like we're going to get a bunch of similar points, weight it based off of how similar they are, and then we're going to train a local classifier, a sparse classifier on it. And the idea is, or the hope is, that just a few attributes might explain your decision surface rather than having to look at all 300 attributes that you might have. Here's a visualization that I find helpful. We see that this red point is our query point. We train a local model on it. We can see that we can get a linear boundary. And there's a citation. It's a great paper. You should check it out. We have a sort of straightforward modification to this. So instead of training it on like a class-wise probability that we're trying to explain, we're actually looking at this concept of certainty when we're trying to explain certainty with sparse labels. So certainty in a binary sense is related to sort of your max class-wise confidence. In a multi-class sense, it's a little bit different, but it basically just means like if we give you a prediction, how certain are we that our prediction is true? And so we're going to do everything based off of that. Lime, the original paper, suggests how you might use it for regressors. I think the actual GitHub code base supports it now too. At the time, we just made some straightforward modifications to the code base, and that's what we're going to apply to the concept of certainty. Say we have a query point and we want to explain why we're certain or uncertain about it. We're trying to maximize uncertainty in a lot of active learning strategies. That's one thing I might have forgot to mention. So I'm just going to sort of walk you through our strategy for this with an active learning experiment on the ProPublica recidivism data. So the ProPublica recidivism data sort of looks like this. We have a bunch of attributes. And basically the goal of the data set, I should mention, is to explore these recidivism recommendations and scores. In this experiment, we're just sort of using it to predict recidivism as the problem we're looking at. And we want to see if active learning can sort of help us achieve fairness or something like that. I'll kind of get into it. But see, we have an example data point. So we have a 34-year-old African-American male with two juvenile felonies, 1 juvenile misdemeanor, 21 recorded priors, and the current charge degree is a felony. And we want to know whether or not this person is likely to be arrested again in the next 2 years. Quirk of the data set is that it deals with people that are arrested again. There's a lot of societal things tied up in that, but without getting in the weeds too much, we want to know what the probability that they're arrested again. So we train a classifier on sort of the attributes we're allowed to use. We don't use race, but we do use the other attributes in the data set, which I think ethically people agree that you can sort of use in sentencing and probation and stuff like that. And we're 88% certain about the specific classification. So that's regardless of sort of whether we think that this person's going to recidivate or not recidivate. We are 88% certain that whatever classification our classifiers come up with is correct. Because I set this example up and I wanted it to be like an intuitive example. This is an example that I picked randomly out of the highly confident that they would recidivate. And then we can use Lime to get an explanation of why we're so confident. This is an explanation of why we're confident, not an explanation of why it's a given class. And we're so confident because they have greater than 20 priors. So that's a bin that we've predetermined in our data set. And it seems kind of intuitive to us, right? If someone, I think it was 21 priors. So if someone has 21 priors on their record, it seems more likely than someone with 0 priors that they might recidivate. We also see that sex male makes us a little bit less certain, and we went through the data and just sort of dug around, and we just found that there's a little bit less mutual information between knowing that someone in the data set is a male, labeled a male, and whether or not they'll recidivate. But sort of over the long term, what we're interested in is systematic bias. So we might have a query point, and we might be able to explain why we think that would be a useful point to learn about. But over the long term, sort of our contribution is defining this notion of uncertainty bias. And uncertainty bias basically means, over the long term, we can look at this active learning problem. We're getting better at predicting for all protected subgroups, but are we getting better over time for a certain subgroup over another? And is this sort of disparity exist in that sense? And the other thing we were interested in is we tried a couple different data sets and we were wondering if active learning, rather than a pre-processing step or post-processing step, if maybe we could just throw active learning at a problem and get a more fair subset of the data. The intuition being that if we're maximizing for uncertainty, if we're uncertain about a certain subgroup, maybe they'll be sort of over-pulled from until we've sort of reached parity. So we did this on, there's the formula. So we did this on the ProPublica data set, and this is sort of just a single run. It's a little bit of a noisy problem, but I can sort of try to explain it. We start off with 500 initial labeled recidivate, not recidivate data points, and then we actively query 2,000 more points. And so this starts out, and there's relative parity, right? There's low uncertainty bias. There's some bias in favor of sort of white people in the data set that matches ProPublica's findings, which is basically that black people were some of the prediction, like the way that mistakes were made in a different way between black people and white people. So just to sort of explain over time, this active learning strategy that we use actually increases the disparity between black people and white people in the data set. And we actually find that like this becomes pretty significant over time. This is not to say that we're becoming less certain about the black people in our data set. We're becoming more certain about all the subgroups in our data set. But relative to one another, we're becoming more certain about the white people in our data set as we label more data points than we are about the black people in our data set. And this is sort of not an artifact of like the different ratios of people in the data set. I think that there's about 3,100 about 3,100 black people in the data set and about 2,300 white people, or 2,100 white people. And we see that they're polled, especially in the beginning, at similar proportion when this disparity really forms. Over time, we see that the uncertainty bias sort of levels out and we start pooling black people at a slightly higher rate. This sort of makes sense, right, if we're overall, on average, more uncertain about those points in the data set. But overall, like active learning did not give us an easier solution to this specific problem. And there's sort of a green line here that represents the people labeled Hispanic in the data set. That just represents a much smaller population than the black people or the white people in the data set, and so that line tends to be a little bit noisier. And then the other question that we want to look at, especially from the chemistry side, is can we automatically generate classes where no like sort of intuitive protected subgroups exist? And so for that, we want to think about like what sources of uncertainty are there, clusters or areas of uncertainty, certain subproblems or concepts that we're learning. And like maybe if we can identify those, we can sort of really drill hard on those and we can understand what the strengths and our weaknesses of our classifier are over time better. So this is a fairly, so this is what we're going to do with that data set. We're going to take a labeled pool, we're going to take an unlabeled pool, train a classifier on the labeled pool, and then generate Lime explanations of uncertainty on all of the unlabeled data points. And then we're going to just run k-means clustering. Sort of prior step to using Lime is that you bin the data set, the attributes for a data set. So we're clustering on those. So we have consistent bins that we can track over time, cluster-wise. And so I was super excited about this. The number one cluster turns out to be just like many sources of uncertainty. So it's a 300-dimensional data set. And so there's nothing that like really explains a majority of why we're uncertain about the data sets, the data points in that cluster. Like I think it's more than 5% is the cutoff. So that's sort of what you would expect. It's kind of disappointing in that sense that that's the most populous cluster, but two very closely related clusters sort of are explainable with just a few attributes. I mean, this third most queried cluster has 4 attributes, which explain about 50% of the mean uncertainty for the data points in that cluster. So we can look at, I mean, sort of it might not be interpretable to you because you guys are not chemists, but I did ask chemists why this might be happening. These two very initially explored correlated curves represent sort of very standard reactions. The beta set is really skewed towards success. So these are reactions that were sort of like not obviously successful, but probably successful. We explore them very thoroughly. And then we sort of, as the uncertainty bias goes down for them, we start to explore these low time, low temperature reactions, which low time, low temperature in these syntheses means that there's just less opportunity for them to be successful. We lean towards thinking that they're not going to, like we start off pretty confident that they're not going to be successful. Over time, we become more uncertain. And so this kind of fits our intuition, is like we explore the problem that's like sort of more tractable first. Our expectation of error reduction is better. And then we explore sort of the harder problem that we might be initially more certain about. And these classes like maybe are not necessarily super interpretable, especially if you're not a chemist. But the idea that we can track these common sources of uncertainty is really the value add here, I think. It's basically like, you wouldn't spend this amount of time for a single data point to explain like why something is uncertain, but if you have 500 data points and they all have this common source of uncertainty, you can investigate that a little bit more and get an idea of like if there's a human intuitive problem that you're solving as you explore that cluster. So just sort of in conclusion is that we try to give you a way to explain individual active learning queries with the application of Lime. We propose related strategies for understanding the change in weaknesses and strengths. That's the automatic class generation. And I think that sort of one of my favorite parts of this work was the development of the uncertainty bias metric, which was based on disparate impact. So you can apply sort of the 80% rule to it. It's sort of related concepts that you can track how your active learning algorithm is doing for important subgroups in your data set relative to each other over time. And it's sort of invariant to the fact that you're becoming more certain about all data points over time. So with that, I want to thank people that have supported my work, including my lab at Haverford. And if anyone has any questions, thoughts, I welcome you to email me. I guess I can take a few right now, if that's okay.
Hey, thanks for your talk. So I'm curious if you had much luck sort of trying to decipher why between blacks, whites, and Hispanics there were such different levels of uncertainty, and like what features of the data might be contributing to that. One sort of first pass hypothesis would be that maybe arrests actually sort of mean less in the black population, because we sort of know that the standard for an arrest is very different among that population versus the white population. So maybe there's less information embedded in saying that someone's black person has been arrested 10 times versus a white person. But I'm sure there are lots of other reasons why that could be. Is that something you've looked at all, or do you have sort of any guesses or intuitions or findings about that?
Yeah, I mean, it's such a messy problem, right? Especially with this real world data set that there are any number of really messed up explanations that we could come up for this. Really the point of this is if you don't if you don't enforce a fairness invariance, it's not going to become fair. It's not going to, it's not going to level out over time. The problem won't take care of itself. So you have to do some pre-processing or post-processing.
Hi, thanks for a great talk. I'm wondering if you think that these kinds of methods like k-means clustering could be useful for cases where, which is quite often the case, where a modeler doesn't have access to the protected attributes of interest, but they might want to do a bit of initial analysis to then go and confirm whether the clusters that they've found might be reflective of protected classes. Do you think that's a general kind of method that you could use for this kind of thing?
Yeah, I mean, I think that sort of what we do here, if I'm understanding your question right, is that we're doing things based off of just certainty and uncertainty. So you don't actually need access to the original data set to understand sort of how a classifier might be, like the things that it might do poorly on, sort of just to get a general human interpretable idea of like, this is what it does wrong, or this is what it does now that it didn't do before. So in that case, I think it's useful in that you can provide these explanations if people don't have access to the data or the internal logic. You can just sort of provide these general trends, which is, I think that's sort of what you're...
Hey, I was wondering, I've been doing some work with active learning, and it's extremely finicky, and almost no result holds up across different acquisition functions, different data sets, different models that you're applying on top of. And I was wondering, I just took a glance through the paper, so maybe I misunderstood something. It seems like the notion of uncertainty that you're using is you're relying entirely on the aleatoric, but not the epistemic uncertainty. So like you're looking at the probability of just like the output of the model, like is it, how far from 1 is it? Or it's 0, right? But that's not the only notion of uncertainty, right? So like if you had something like a Gaussian process, then it would say, I'm uncertain about data points that are very unlike the data points that I've seen. And not just looking at, what your model outputs for a data point that it never would have seen based on what you've acquired so far. It might be really confident, it might not be, but that's different from the kind of uncertainty because it's an unfamiliar data point. So I'm wondering, like, have you looked at this through different acquisition functions and different notions of uncertainty? Because in a way, you'd think that active learning would actually be really good here in a way, because it sort of encourages you in a way to pick or the common approach to acquisition functions is you should pick points that are unlike the ones you've already seen. So you would expect at least under some kind of acquisition function, it might actually have the opposite effect.
Yeah, so actually, thank you for that question. Yeah, so the ProPublica data set, it was sort of a binary question, classification problem in this sense, for just like illustrative purposes. Is that how you say that word? But sort of the chemical problem is that we've really been sort of digging into it right now, because you can't sort of think about like a real chemical space, like you have 2 points, like you can't think about a Euclidean distance between them being a good similarity metric. And so what the things we've been looking at is like if we sort of take these data points far, far away from the initial data points that we have, which are active learning algorithms, like we're really uncertain about this, like we really like these points, we want to query from them. We've been doing a lot of sort of trying to understand how this works for things that are like well beyond your data set. So I think that's a good line of inquiry that we're actually attacking right now. And I would actually be super stoked if you wanted to talk about that more, because that's sort of the current practical problem that we're dealing with.
All right, let's give a round of applause again.